So let's start. Welcome to the One Word Mathematical Physics seminar run by the International Association of Mathematical Physics. We are happy to have today Leon Loveridge from the University of Southeastern Norway, who will tell us about operational quantum reference frames. Please go ahead.
Right. Well, thank you very much for the introduction and also, of course, the invitation. It's very nice to speak in this series. So I notice there are plenty of people in the audience who already know quite a lot about what I'm going to say. So they should feel free to speak up and object or ask questions as I go. I guess that's the style, right? Is that we expect interjections. So I'm very pleased to take them as they come. So I'm inviting people to join some research on quantum reference frames, which has sort of gained some interest of late. And the way that I decided to do this talk was to sort of chart my way into the subject of quantum reference frames in the topic of more like quantum field theory. But I started out in quantum mechanics and in operational quantum physics. So I'm going to start from there. The talk is a little chaotic. This is a reflection of my mind. So please do stop me if I don't say if I say something that sounds confusing. So I start with trying to frame why we want to speak about quantum reference frames in the first place. And I think this is one place where there's many answers. So one, I think, reasonably compelling motivation is to say, okay, well, consider the following three statements. Quantum mechanics, or perhaps quantum field theory, reflects our experience of the world in a precise and accurate way. So we do measurements and so on, we build theories, and we can confirm it in experiment. Secondly, more controversially, perhaps quantum mechanics is universal, so it describes everything. And thirdly, the things that can actually be measured in nature are invariant under, I've just written XXX, this might be symmetry transformations, it might be gauge transformations, and so on. I leave that open for now, because it's just supposed to be a vague motivation. But one immediately sees there's something of a tension here. So, we're used to thinking of fundamental particles as being somehow associated with irreducible representations, usually of the Poincare group. And of course, well, irreducible representations, what's invariant under that? Well, essentially nothing. So we don't really have a lot of observables. So one thinks, well, how is it possible that we have a rich observable structure that we actually genuinely see in the world, and yet we want observable quantities to be invariant under gauge or symmetry transformations? So I would argue, well, what we're actually observing is not the systems in themselves, but the relation between a system and some reference frame, some apparatus, something like this. So that's one way of thinking about it. There's another way, which is just to sort of follow Einstein completely in his quest to understand relativity of space-time theories by thinking about clocks and rods as being described by physical systems. And one actually gets a much more compelling description of nature if one takes these reference frames seriously and describes them as, well, if one describes them with the same theory as one describes a system relative to which, or to which they are being described relative to, if you see what I mean. So if we want to describe relativistic systems, we should think about clocks and rods that are in Minkowski space. And if we want to describe quantum systems, we should think about reference frames as being described by quantum systems. I think there is still some work in trying to come up with compelling motivations that is acceptable to everybody, but at least I'm convinced. So I'm going to talk about one framework called the operational framework, which is motivated by what I'll call operational quantum physics, which I'll describe in a minute. But there are many others. Okay, so there is the perspective neutral framework, there's the extra particle approach, and there's some other work being done. So somehow this is a subject where everybody's sort of moving in the same direction, but it's not sufficiently mature that everybody has completely the same starting point or the same set of assumptions and so on. So I will talk about two recent uses of this framework that I'll briefly mention these novel uncertainty relations that one gets if one takes quantum reference frames seriously. And then I'll focus a bit more on this thing called type reduction in algebraic quantum field theory, where we introduce reference frames in a space-time relativistic setting. So I'm going to start from the very beginning with operational theories. I don't know everybody's background, so I think I might as well start right from the start. So there's a general way that one can think about operational theories in terms of the most basic experiments. So we think about preparing some system many times, and we think about measuring it many times, and we can just collate frequencies. So for each outcome, we'll take capital omega as being just some finite set for now. We can write down the frequencies and we can approximate the probability distributions as the long time frequency limit. So, we can call the preparations states, we can call the measurements observables, and we can call the assignment of some state to each possible outcome and effect, and so on. So we build up this probabilistic structure. And then we might want to say, well, we can mix preparations or states. We can prepare in one way with some probability and some other way with some other probability. So we want to have some convex structure. We want the effects to respect the convex structure. So we want them to be at least inside the affine maps on the set of states. And then we can turn it around and say, well, if we have this structure on the set of states, we might want some linearity on the effects and so on. And we get this sort of state effect duality in this finite regime. One can do better. One can take, this is very much a side comment at the moment, but one can take the state space to be some generally convex subset of some real vector space. And with some additional conditions, one can get these things called base norm spaces and order unit Banach spaces, where one already feels like one's getting quite close to quantum mechanics in some way. So I think the main point of this slide is to say, well, I think we could have discovered quantum mechanics in this way rather than through, say, quantization or something like this. So as an operational theory or a probabilistic theory. So we can think about observables as just the assignments from some possible outcome of some experiment to some effect. Call it an effect valued measure. And since we have a convex set, we can talk about the extreme points and so on. It's non-empty. And we have this general structure. So of course, classical probability theory is one example. States are probability measures on some outcome set. Pure states have some special properties. They're delta measures. And I'd say the primary geometric difference between quantum mechanics and classical mechanics is that the state space in classical theories are a simplex. So you can decompose any states into pure states uniquely. We can think about observables in various different ways. But since we have a convex structure on the set of effects, we can think about the extremal effects, and these turn out to be idempotent, and they're therefore essentially projections, characteristic functions, and so on. And if we can reconstruct real valued functions from this structure, and we have the standard sort of Gelfand duality in this classical world. So we have something like a commutative C-star algebra of classical observables, which are a special case of this more general structure. Of course, quantum theory is another example, so I can use this even to fix some notation. So quantum theory, we have a Hilbert space, and we have the trace class, and we have inside the trace class the states, so the trace one, well, the normal states, trace one positive elements, which of course we have again this duality structure. So the trace class is the pre-dual of the space of bounded operators on the Hilbert space, and so on. We have pure states as the rank 1 projections, effect operators in the unit interval, and observables are identified with the positive operator valued measures. So if we have our outcome space omega and some sigma algebra of subsets of omega that represent our the events, if you like, that are observable in some experiment, we have an assignment which just gives an effect for each possible outcome. And there are some additivity requirements and so on. with sharp observables, I'll call them. So these are just the ones that are given by positive operator value measures that are also projection valued. So one then therefore gets back the standard description in terms of self-adjoint operators and so on. So I'm being more general, and it's crucial to be more general because some of the main theorems later require that our observable structure is more general than the set of self-adjoint operators. Of course, we have the Born rule probabilities. In fact, POVMs, positive operator valued measures, are defined exactly so that the sort of standard Born rule probabilities are given when we trace against a state, or even more generally, just some algebraic state on the algebra where these positive operators live. So my point of view again is that, well, if we discovered quantum mechanics in a different way, we would have discovered POVMs as the right description of observables from the very beginning. They're somehow inherently part of the probabilistic structure of Hilbert space. And there's a simple to prove but nice, maybe underappreciated theorem that tells us that, well, if we have a positive function on some sigma algebra values in the positive operators, well, this map is a POVM if and only if the standard if it reproduces well, so if X is a unit vector in the Hilbert space, then E is a POVM if and only if this assignment is a probability measure. Okay, so there's really a one-to-one correspondence between Born rule probability measures and POVMs acting in the Hilbert space. So my view is that it's a historical accident that we chose self-adjoint operators to represent observables, and it could have gone the other way. So as I say, the POVMs, one of my goals today was to convince people that POVMs are the right way to think about observables in general. So I'm going to list quite a few examples in a minute to hopefully convince you, and then move on to some other things, QRFs. But they fit with the natural probabilistic structure of Hilbert space. They arrive naturally in measurement. In quantum mechanics, one can read the work of Bush and collaborators, and in QFT, more recent work of Chris and Reiner, one of whom may or may not be in the audience, I'm not sure. There's a misconception that POVMs are just somehow worse versions or the sort of snotty-nosed little brothers of self-adjoint operators because they just introduce some classical noise. But I think that's not right. There are POVMs that arise sort of intrinsically that can't be viewed as just some sort of muddled version of some projection valued measure. An example that we'll come back to is that one can get, say, a better definition of incompatibility. So if one remembers that we usually call self-adjoint operators compatible if they commute, but there's a more general operational or probabilistic way to describe this. And we say that, well, suppose we have two POVMs, A on some outcome set omega A and B on some outcome set omega B. Well, these are called compatible if and only if there's what's called a joint observable on the product that gives these two POVMs as marginals, right? So we just sort of average in some sense over all of the stuff that we're not looking at on both sides. And if that's possible, we can call them we can call the A and B compatible. They don't need to commute with each other. Okay, so it's much more general. If one of them is sharp, then it's equivalent to commutativity. But if both of them are unsharp, then it's certainly more general. So we're moving now towards covariant POVMs. So these are the ones that are that interact nicely with a representation, say. So well, let's have a look at another motivating reason for looking at POVM. So if one goes back to the Pauli theorem, which is essentially the Stone-von-Neumann theorem, one knows that the canonical commutation relation is essentially unique. So of course, therefore, given some self-adjoint operator A, whose spectrum is bounded from below, then there's no self-adjoint B, which is canonically conjugate to it. So that's no good if we're looking to describe, say, time as a quantum observable, or phase, or so on. So this is equivalently saying that there's no projection value measure on the real line, which transforms covariantly under, say, translations in some variable t generated by A. But there are many examples of POVMs that do have this property. So if one fixes some A and says, well, is there an EB that is covariant under this unitary conjugation? The answer is often yes. Not always, but often yes. So one example is that if we take, say, the number observable, if you want to call it that, so something like the harmonic oscillator Hamiltonian, this is of course bounded below. We just count positive energy modes, if you like. So there is no phase conjugate to n as a self-adjoint operator, but there are many POVMs that are conjugate to it, and you can construct them rigorously and explicitly. So this is one example. So we have this phase observable, which is rigorously defined and covariant under translations generated by n. Okay. So there are many POVMs in this talk. This one is an important one. So another example is to take, well, we can call it a Hamiltonian. For those in the know, you'll know why I'm doing this. So we just take the multiplication operator in L2 of R plus or some dense domain. And we want to say, so it just multiplies by the coordinate in L2 of R plus. And we want to say, well, is there a conjugate quantity? And the answer, of course, is no by Stone von Neumann. But there is a covariant time observable as a POVM that eats Borel sets of R, gives us something in here, and transforms covariantly under this Hamiltonian action, if you like. So little t here is time. And the construction is canonical. So one can just embed L2 of R plus in L2 of R, take the momentum conjugate to the extension of Q plus to the standard position operator Q in L2 of R. That gives us a Fourier pair. And then we project back down or compress back down from the embedding, and we get exactly this ET. So this is an example of what's called a covariant Neumann dilation, and these always exist. Okay, so as I mentioned, endless POVMs. Here's another one. So we can take the spectral measures of position and momentum, and we can say, well, we know these are incompatible as self-adjoint operators, but are there somehow smeared out or unsharp versions which are compatible in the sense that I mentioned at the beginning? And the answer is yes. One can choose any state as a density matrix T in the Hilbert space L2 of R. The W of Q and P are the Weyl operators, and one can just sort of move them around in phase space in this way. So we're constructing what's called a covariant phase space observable, GT. So Z is a Borel set in R2, and these have marginals which are smearings of the PVM corresponding to position momentum by some probability measure, mu t and nu t, which can be obtained from a formula. And from here, one gets more general uncertainty relations that are more stringent than the the standard ones, say the one where you have a half on the right-hand side. Okay, so that's a covariant phase space observable. More relevant to what I'll say later is a unsharp observable that comes from Tomita Takasaki. So this is, I'm not an expert on exactly how these can be constructed in general, but one example, and the tail is maybe wagging the dog here. So let me just go through the standard stuff about Tomita Takasaki. So suppose we have some von Neumann algebra M, and say a KMS state, or a faithful normal state on the algebra. As is well known, one can then construct what's called the modular operator delta. So this is in the world of Tomita Takasaki theory. One actually obtains something like a closed positive self-adjoint operator, and one closes it, and one does the standard things with the modular conjugation and so on, and one gets a positive self-adjoint operator as follows, called the modular operator. This depends on the state. So we're doing functional calculus here, but somehow not strongly. So this is up to a con cocycle. So this is the point here is that von Neumann algebras come with some sort of well, intrinsic dynamics in some sense. So given a von Neumann algebra and a faithful normal state, one has a one parameter group of automorphisms of the algebra, and the magic of this theory is somehow that this operator is always in the algebra for all times. Um, so one has some dynamics associated with the von Neumann algebra, associated with a state, which is sort of nearly unique. And of course, the magic of this is that it goes the other way around too, in some sense. So if we have some one parameter automorphism group of a von Neumann algebra that satisfies, well, this invariance condition and the standard KMS condition, then well, modular automorphisms and the existence of a KMS state come hand in hand, essentially, is the point I'm trying to make. So the KMS states are related very closely to these modular automorphisms of our von Neumann algebra, and that will come in handy a little later on. So one can say, okay, well, suppose we have our modular automorphism group acting on our von Neumann algebra that's, say, represented in some Hilbert space. What is the time as an observable corresponding to such an automorphism group? And there's some work, and I'll go to the references at the end, suggesting that typically, or at least in some cases, this is genuinely an unsharp observable. So there's a POVM that's generated by this group of modular automorphisms, which I think is really interesting and somehow underutilized or little known. And there's a lot to be done to understand this more generally. Okay, I think I will skip this slide. I'll just give a highlights reel. So POVMs also arise in measurements of quantum observables, and this has been extended recently to AQFT. I guess not that recently anymore. I'm showing my age by Chris Fuster and Rainer Wersch for measurement schemes in algebraic quantum field theory. But there one sees also that POVMs arise naturally in the measurement schemes. So let's go to quantum reference frames. So how do we motivate it? So for me, the general principle was that what can be observed in the world should be invariant under either gauge or symmetry transformations. So for example, the standard example would be something like, I just noticed there's a lot in the chat, but I guess I don't need to deal with that.
You don't have to care about chat.
Okay, good. Thanks. So let's just take it seriously. So if one's doing ordinary quantum mechanics, one understands that, well, the position of a quantum particle is not really meaningful, but really it's the relative position of two particles, or the relative angle between two quantum systems or something. Well, if we want to sort of respect, say, Galilei or Poincare invariance, we don't want to say that the position, the absolute position, is a meaningful quantity. That somehow violates isotropy, homogeneity of space-time. But we do know that there are relative quantities that relate some systems to others that are invariant. For example, the relative position is a translation invariant quantity. So as I mentioned at the beginning, if one has a group which will be, for us, always locally compact second countable, so that would be, say, our symmetry group, with some unitary representation in our Hilbert space, well, if that representation is irreducible, then there's nothing left by a Schur type lemma, right? So this says we can't observe single particles. Well, we think that's probably wrong. So my claim is that, well, invariance and, say, the relativity in terms of relative quantities are intimately connected in relativity theory. So we're just going to reimpose our invariance hypothesis, not at the level of single systems, but at the level of compound systems. So we say we just introduce a second system that we're going to call a reference frame. In there, we can talk about relative position, relative phase, relative time, relative angle, and so on. And these are G invariant quantities. So then one has a bit of a conundrum. Well, how are those two theories related, right? So how is the standard quantum description and the invariant description related, and how are the predictions that we make reflected in the invariant description, if that's what we believe is fundamental? So inside the invariants, so we have Hilbert space, bounded operators, G invariants. So by superscript G, we'll always understand that that is coming from U, some irreducible, so some unitary representation for now. And inside here, there are going to be some special observables that we think about as relative. So I'll provide the construction in a moment. Now, there's a bit of a divergence of attitudes here within the community. So if one has, say, a locally compact but non-compact group, typically one might have quite a lot of invariance in B of H, but one might have no genuine invariance in the state space. So our approach is to say, and some approaches sort of use a rigging construction or something to say, well, we can construct maybe non-normal invariant states, or we can understand these states distributionally. In this approach, we don't do that. We just say, okay, well, what we're going to do is identify states that agree on the invariance, and that's going to be our state space. So this is a structure that's not well studied, but we have some insights into the structure of this thing. So it's a bit different from what you see anywhere else, as far as I understand. So how do we do it? How do we build these invariant quantities? Well, we introduce a quantum reference frame. So after many years of not defining them, we eventually did define them. So a quantum reference frame is essentially nothing but a covariant POVM for us. So we have a group action acting on a homogeneous space of the group. So sigma is some homogeneous space. Our quantum reference frame E, sorry, there's a typo here. So E and ER will be the same object here, which takes measurable sets of our homogeneous space, gives us effects in the relevant algebra B of HR. So it's a covariant positive operator valued measure. It is possible that one can go a little bit more general than this, but for us, that's exactly what it is. So, of course, one has a bit of a taxonomy. So it's not crucial that we look at all of these in detail, but we'll call it sharp if it's projection valued, principal exactly when sigma is a principal homogeneous space for the G action. Ideal just incorporates the first two. Important for this talk, compactly stabilized exactly when the homogeneous space is a quotient of G by some compact subgroup. Localizable, I'm going to come back to that in a minute. Complete, we won't need. Coherent states, we won't need. But the point at the bottom is important. So covariant POVMs can be related to standard covariant PVMs through this dilation theory that I mentioned earlier. So I'm going to introduce that in a moment. But first, I'm going to introduce what we call this relativization map. So the yen map. So I think there are at least a few Japanese in the audience who hopefully will be pleased by the nomenclature here. So this is actually due to Takayuki Miyadera. So he visited York in 2010, and we were trying to understand some older work on quantum reference frames in the quantum information literature, where they had a dollar map that somehow was useful for them for writing down invariant operators. And we thought we managed to do a better job of writing down the appropriate map in a more general way. And Takayuki provided the formula, and Paul Bush suggested that we should call it the yen map. So 15 years later, it's still the yen map. And I won't comment on the exchange rates or anything like that. But it's here to stay, I think. So what does it do? So we have some unitary representation of our symmetry group G acting on both the Hilbert space of the system, that's B of HS, and the Hilbert space of the frame, that's B of HR, and that acts diagonally by conjugation. We can make this more general, but this is the gist. ER here is our quantum reference frame. So this is covariant. So what we do is we input a self-adjoint operator, or generally a POVM actually, just by composition. and we sort of smear it out and tensor with this E of dg. So this is an integral that makes sense. It lands in the invariant algebra. That comes directly from the covariance of ER here. That's just a simple computation. So yen is linear. It preserves the adjoint. It preserves the unit. It's contractive, so it's norm non-increasing, positive. It's a normal map as a map between von Neumann algebras. And if E is projection valued, then it's an injective star homomorphism. So somehow just gives you literally a copy of the original algebra inside the invariant algebra. Otherwise, it's not. Otherwise, it satisfies all these other conditions, but it's not. It doesn't preserve the product, which isn't really a huge issue for us. One can make it more general, so we can also define it on compactly stabilized compactly stabilized quantum reference frames. So replacing G with a homogeneous space of G. Then one has to make some more conditions, but everything is sort of okay. So we can take the image of this map. We may have to close it up in the ultra-weak topology on its image. We talk about these as relative observables. The naming is, I think, reasonable. For example, if one just takes G to be R, that's the group of translations on the real line, generated by, say, the momentum, and one puts in the position or its spectral measure, one literally gets out the relative position. So it sort of does what we'd expect it to do on familiar cases, but it works obviously in general, also for time and phase and angle and so on. So we think that the image of this map has some special status, is giving us something like system relative to frame, and it doesn't exhaust the whole invariant algebra. So there are invariants that somehow don't have this relational property. One can sort of do a sanity check that this is a good theory. So it turns out that we can also identify trace class operators that agree on the image. And very nicely, I think it turns out that that is isomorphic to just the pre-dual of the algebra, or even just the space of relative observables. So one has this state observable duality, if you like, even in this relational world. Okay, so one can also define relative states inside the trace class here. And this is the point of departure for some other approaches to quantum reference frames, which I won't say too much about. But it took us some time to understand that some approaches to quantum reference frames start with this idea of states relative to other systems as being somehow intrinsically given or as part of the defining data of the theory. And I didn't quite understand that. So we wanted to understand how can we make this rigorous within this theory, and it turns out that you can. So yen is normal, so it has a pre-dual, and its image turns out to be actually isomorphic as a Banach space to the quotient here. Okay, so we have the relativization map. It has some good properties. We also want to say, well, what happens if we're given the compound system? How do we restrict? How do we say, let's fix a state of the frame and just forget about the frame, sort of externalize it and just talk about the system? So here we have the restriction map. It has a canonical, a straightforward definition. We take tensor products in here, and we just take A as given and trace against B. So this is what's called a non-commutative conditional expectation. In the sense of von Neumann algebras, it's completely positive and so on. And we view it as sort of, it really is a sort of conditional averaging. So we fix a state of the frame, omega. So omega is a state of the frame. And then we can just describe the system on its own, sort of relative to that preparation of the frame. So one can then, of course, look at special observables inside there by first relativizing, then restricting, and say, well, what theory do we get? And does it make sense? And the answer, I think, is yes. So for example, if our original observable is invariant and we relativize it with yen and we restrict back down again, we just get the same observable for any frame state. So this is just saying to me that invariant quantities are defined relative to any frame. So they're frame independent, if you like, which is what we wanted kind of from the start. We want to say that the invariant structure is somehow the frame independent structure. One can do various other things. I'll skip out this isomorphism, but one can say, well, if we fix some frame state and we take the pre-dual of our relativization map, we can say, well, this is our state relative to the frame state. So rho is our system state relative to omega, our frame state. And we get some sort of active passive equivalence here. So if we move our frame state around by g, it's the same as moving our system state around by g inverse. So this all makes sense, I think. And then there's one more important property that a frame might have, which is this localizability condition. So there's something called the norm one property. I don't need to give the definition, but it says that if our frame effect is non-zero, then there's a sequence of states where we can take the large n limit to give us probability 1 on any set x. Okay, so this is something called the norm 1 property. This is satisfied by all PVMs, but certainly not by all POVMs. And then we could say, well, this answers the question that I motivated in the beginning. So what is the relationship between the usual theory that we're used to using, which is ordinary quantum mechanics, or maybe ordinary quantum field theory, where we have the bounded operators on the Hilbert space and perhaps no symmetry group, and the symmetry invariant theory, or the relative theory, where one is looking at system relative to frame. So I think this is, or at least for now, the most important theorem in this approach to quantum reference frames, which is that if we have a localizable principal frame and a sequence of states that can be arbitrarily tightly localized around some, say, Borel set, or some measurable set in G, then we can, for any AS of the system, we can relativize it and we can restrict it, and we get the same AS back again. So we're saying that the two theories have the same probabilistic content, provided the frame has this very special property that it admits these localizing sequences of states. So I think that in quantum mechanics, one can always do it. One can just build, say, the canonical frame, which would just be L2 of the group, and the standard PVM on L2 of G given by left translation. And this is in some sense saying that, well, we know that in that case, the relativization map is an algebra homomorphism. So that algebra is already in there somewhere. So we're just sort of finding a way to get it back again. But there is a converse that says, well, if the frame is bad, there is strictly a discrepancy between the relativized restricted observable and the observable in general that you started with. So this tells me somehow that ordinary quantum mechanics doesn't tell us about the quantum system in its own right, but it tells us about the relation between some quantum system and, say, some suitably classical reference system, some large reference system, because we know that to have these localizing sequences, we have to have, in some sense, a big frame. Okay, and this is not possible for bad frames. Now, in quantum field theory, things are more difficult. So one has much more constraints on the frame. So I think it's quite likely that it's not possible to build frames in general that have this nice property. Okay, so that's what I'm going to get onto quite soon. I'm going to skip this frame relative uncertainty relation in the interests of time, but have a look at it on the you have the slides. So if this is interesting, please just send me an email. So I'm going to get on with the AQFT part of the talk. So this is applications 3. I'm not entirely sure what 1 was, but that doesn't matter. So this is a recent application of this particular framework of QRFs. There are other recent applications too, which I can direct you to at the end. So algebraic quantum field theory. What is the data? Well, we have some, say, Lorentzian manifold with some regions. I'm not going to say too much about what they are. We have some von Neumann algebras. I'm not sure what this little m is doing. That's a typo. Von Neumann algebra is attached to some regions. that satisfy, well, the association between the region and the algebra, of course, satisfies some axioms. Now, in terms of the algebraic structure of these local algebras, of course, it's known much better by some in the audience than by me, the reasons for this, but these are typically type 3 von Neumann algebras, which are quite wild operator algebras. So what do I mean by that? Well, we'll have to go through and talk a little bit about what we mean by types of von Neumann algebra. I'm just going to have a quick sip of water. Okay, so types of von Neumann algebra. So somehow in physics, well, as we all know, if we talk about, say, quantum information systems, we like to think about Hilbert spaces as say, tensor products of qubits, say C2. So we have some overall total Hilbert space, which is just the n-fold tensor product of some basic system, and our von Neumann algebra is just the matrix algebra over the complex numbers, n by n matrices. So then one gets a little further and says, well, what about wave mechanics? Well, we have L2 of R would be the classic example of von Neumann algebra, just say the bounded operators on there. So this is something called type 1 infinity. And we can get more and more complicated. So every von Neumann algebra, or every factor, so every von Neumann algebra which has trivial center, is one of these types. There's a lot of interesting mathematical work in constructing the various different types. So, for example, groups that have this ICC property, that's this infinite conjugacy class property, have group algebras that are type 2-1 von Neumann algebras. In physics, they occur somehow as infinite spin chains. You can then build two infinities out of tensor products of these. And then in sort of increasing order of richness, at the end, the maximal richness or pathology, one has quantum field theory, which are type 3 von Neumann algebras. So these are unwieldy objects. They can be constructed in some way via an important construction called the cross product construction, which I'll come back to. So one could, for example, take a 2 infinity and take the cross product with R for some suitable action and get the type 3. So luckily, there's a good characterization of these by these trace maps. So a trace is exactly what you'd expect. It's a map on, say, the positive elements, possibly non-finite values infinity, that have this unitary invariance. So it's homogeneous and additive and so on. And of course, we would call the trace finite if it's never infinite, and semi-finite if we have a dense set with finite trace and so on. And if it's finite, then we can extend it to the whole algebra in this cyclic way. So that's the standard thing we're used to doing under the trace, cycling it around. So the full characterization of factors comes from the value of this trace on the projection lattice of the von Neumann algebra. But let's just, oops, let me go back. How do I do that? There we go. So type 1n finite trace, that's just literally the sum of the diagonal elements of your matrix. Semi-finite trace on type 1 infinity, that's the usual trace that we use when we're doing ordinary quantum mechanics. 2-1 has a finite trace, 2 infinity a semi-finite trace, and type 3 no finite trace. So this is a bit of a problem if one wants to understand certain quantities that seem to appear in physics. For example, these important and interesting entropies related to black hole or cosmological horizons, the sort of Hawking-Bekenstein formula, the Hawkins-Gibbons formula that relates the entropy of, say, a black hole to its horizon area, right? So that's if one wants to understand that as a von Neumann entropy in algebraic quantum field theory proper, one needs to have the formula where one takes the trace against a density matrix. So that's some motivation. So this is an issue if our QFTs are described by type 3 algebras. So there was this very interesting paper that came out, I guess 3 years ago or so. This is Chandrasekharan, Longo, Pennington, and Witten, where they said, okay, well, let's take our type 3 von Neumann algebra, living in what they call the static patch of de Sitter. So we have the de Sitter space-time, and we take the region that is causally accessible to some observer living on a world line. So this is the region that can be where an observer can influence causally some future and can be influenced causally by some past. So let's just take that as being the sort of the setup, and then they say, well, okay, let's have the quantum field theory into Sitter, and let's introduce an observer traveling along some world line in this static patch, and let's look at the time translation invariant algebra. So they did not say the words quantum reference frame, but to anybody who was looking at it, it was fairly clear that this observer of CLPW is appropriately or canonically or compellingly understood as defining a quantum reference frame. So that's what we did. So FJ, if I may be so bold, FJLRW, this is Chris Fuster, Dan Jansen, myself, Kasia Reichner, and James Waldron, is to say, well, let's take this observer of CLPW seriously, take a quantum field theory in the static patch of de Sitter, and introduce a quantum reference frame. And then we have access to all of the machinery that I've just introduced to analyze the situation that one finds in this setting. So big picture is motivated again by, I would say, symmetry constraints and wanting to understand what the true observable structure is in this setting. So, de Sitter is a symmetric spacetime. It has a non-trivial symmetry group or isometry group for us. So we want to say, well, what are the true observables as the invariant observables or as the relative observables? And what can we say about the algebras? So what CLPW observed was that the time translation algebra, time translation invariant algebra, with a bunch of extra things that I'll mention soon, of quantum field theory plus observer on a world line with a particular Hamiltonian gives an invariant algebra which is not type 3, it's type 2-1. So this has a finite trace, and then one has perhaps some hope of computing entropies. So what we did was we said, right, let's take a quantum field theory on a background with isometries. For us, the isometry group was taken to be R cross something compact. That's as far as we got, relative to some compactly stabilized quantum reference frame. And then we want to say, right, what is the theory that we can write down? What is the type? What are the observables? And so on. So the techniques are based on cross products, which I'll define, or at least explain the use of, and the modular theory that I've discussed a little bit so far, plus the theory of quantum reference frames that I've introduced. There was something else I was going to mention. I do not recall what it was. Yeah, so there are many papers on this now. For us, this is about the isometry group of the background spacetime. You'll see, if I say it carefully, that I don't say gravity at any point. And there's an interesting open question about what is the role of gravity here, because there are other works that claim that somehow gravity is crucial for this business. So keep that in mind, and I hope I say it right. So how do we do this? We have this theory called dilation theory that says, okay, we have our quantum reference frame, which we know is a covariant POVM on some homogeneous space. We want to say, well, we don't know exactly what to do with this situation, but we do know what to do with a different situation, which is just to dilate it. So this is called a Neumann dilation. So all of these quantum reference frames, in some sense, are sub-representations of induced representations. So that's an idea due to Mackey, but the covariant version is due to Cataneo. So we just embed quantum reference frame canonically in some sense, in some new, we define a new quantum reference frame, which is just the most obvious thing you can do. So you could just take lambda is the left regular representation in L2 of G, P is the canonical PVM that is covariant under left translation. So we just essentially build the left regular representation L2 of G, and there's this extra K lurking around, which is part of the construction, but well, it doesn't do a huge amount of heavy lifting. So if W is our sort of embedding isometry, then we have this compression that takes our standard quantum reference frame back to our quantum reference frame. So we can always dilate. In the language of CP maps, this is essentially a Stein spring dilation. So any covariant P of M is of this form. So any quantum reference frame is the compression of some, say, let's call it standard quantum reference frame. And this WW star is what we call a Neumann projection. So what do? We take a quantum field theory described by a von Neumann algebra, MS. So that's given to us. We have our isometry group of some of the background spacetime with some action alpha S on our von Neumann algebra. And then we introduce a compactly stabilized quantum reference frame. I mean, what we want to say is, what is the invariant algebra? If we take our system, our QFT, introduce this B of HR, and look for the invariant algebra here. So we're looking arbitrary action on the von Neumann algebra, but on the quantum reference frame, we have conjugation by some unitary. So it's well known that the invariant algebra of M tensor B of L2 of G under this action is exactly this should be an isomorphism here. Is isomorphic to the cross product. So the cross product is a way of canonically constructing a von Neumann algebra that encodes the action of a group on the von Neumann algebra. So it's a bit like the semi-direct product of groups, but it somehow tells us exactly how the group is acting on the von Neumann algebra. And this isomorphism is well known. So for us, we know how to deal with this case. We don't know how to deal with this case. But we do know that we can do the embedding. So there's our auxiliary Hilbert space K. And one finds that there's an isomorphism that comes exactly from this Neumann projection between the invariant algebra that we actually are after and this thing on the right-hand side. So inside here, there's the cross product, and there's the auxiliary Hilbert space, and there's the Neumann projection that came from the embedding. So we're going to assume that alpha S is unitarily implementable. It's not a huge restriction. And see what we can say about this invariant algebra. Like, what is its type, for example? So as I mentioned, we're going to take our isometry group R cross compact and a compactly stabilized quantum reference frame. Our Hilbert space of the frame decomposes in this way. So this is the constraint that comes from the fact that we have a covariant P of M on the Hilbert space of the reference frame. So we're going to assume that the quantum field theory has a faithful normal KMS state. One can be a bit more general here, but there's no need for us to be more general at the moment. And that there's a modular action coming from the KMS state. And that the modular action is unitarily implemented. And then one gets this following isomorphism. So we have our invariant algebra, and we want to just look at time translation, and one finds that inside the right-hand side, one has the cross product by the modular action. This Hilbert space just factors out, and then we have this Neumann projection. So the point here is that the H being compact doesn't play a crucial role. So once we know exactly how time evolution, exactly what time evolution does to our algebra, we're essentially done. So it's well known that cross products by modular actions of R are semi-finite. So that's in the literature. with a bit of extra work, I refer you to the paper. One can show that the invariant algebra, building on this, so one has to construct a semi-finite trace on this algebra, which one can do sort of out of the semi-finite trace on this modular cross product. The proof is lengthy, but not so tricky to follow, I think. So I refer you to the paper. So one can construct this semi-finite trace, and one can show that it's finite on here. This is a little bit of a mess, I know, but I will give you a reason why it's worth looking at this in detail in a minute. Exactly when the constructed trace has finite value on this projection. Okay, and then one can see that from here, well, we have a subalgebra of a finite algebra, so this is going to be finite. So we have a type 3 von Neumann algebra describing our quantum field theory. We have a quantum reference frame with certain properties. It turns out that the invariant algebra, so the algebra that in some sense says that contains the observables relative to the quantum reference frame, is finite. So it has a finite trace. So we've turned a type 3 algebra into a type 2-1 algebra in quite a general setting. Okay. So I see that I'm running slightly short on time. Now, there is a thermodynamic way of thinking about this, that if there's a KMS weight on the quantum reference frame at inverse temperature beta, that is the same as the inverse temperature of the KMS state that we assumed existed on the original von Neumann algebra, this is a sufficient condition for finiteness. So we're looking into that at the moment to see exactly what the physics is here. So one can write it as a slightly nicer theorem. This still doesn't contain all the adjectives that we need. So I refer you to the paper. So this is reference 3. This is the main paper that I'm basing this part of the talk on, is that if we have a quantum field theory with a faithful normal state, so we just need our von Neumann algebra to be sigma finite with a KMS state omega, acted on by a group which is the form R crossed some compact group, plus a compactly stabilized quantum reference frame, then we have a semi-finite observable algebra as the invariant algebra. Then if some extra conditions are satisfied, this normal KMS weight on the frame, we get a finite algebra. There's some extra conditions. I refer you to the paper. So let's go back to CLPW. This tells us a lot about how this actually works in practice. So we have any old quantum field theory in the static patch of de Sitter. So the de Sitter group is just R cross SO n-1. That's our isometry group. But we're just going to presume that bit acts trivially and just look at time evolution. Okay, so now you see why I had the POVM that I did at the beginning. So we have a Hamiltonian describing the observer, Q plus. So the Hilbert space of the reference frame is just L2 of R plus. Okay, so the Hamiltonian in some units is just given by multiplication on the positive half line. Now we can use our covariant dilation theory to construct conjugate, if you like, a POVM that is covariant under the action generated by Q plus, which is just a Fourier transform of the multiplication by the characteristic function projected back down. So P plus is our Neumann projection. And then you say, well, what is the time translation invariant algebra? And one sees that it takes the form of the right-hand side. So one can see very clearly here that this type reduction business happens in 2 stages. So one takes a type 3 von Neumann algebra, that's our quantum field theory. One takes the modular action of the real line, understood as time translation. So this is, if you like, the restriction of the vacuum to the static patch of the theory, giving us our KMS state and therefore our modular action. And then we have P plus as our Neumann projection. So inside here, we have a type 3-1 or a type 3 modular action, modular cross product, cross product by modular action takes our 3 to a 2 infinity. So that's semi-finite. And then we project back down with our P plus that takes our 2 infinity to a 2-1. So it's a 2-stage process, a 3 to a 2 infinity, and then a 2 infinity to a 2-1. from my point of view, as somebody who has a background in quantum mechanics and operational quantum mechanics, it's sort of fascinating that the Neumann projection, so this compression back to the smaller quantum reference frame, if you like, turns the canonical say momentum into an unsharp time observable. So this is telling us somehow that unsharpness is a crucial property for regularization of quantum field theories in the way that I've described. So we've shown that if you have a von Neumann algebra that's type 3, and you include a quantum reference frame with some specific properties, you get a type 2, which is finite. So there's a finite trace, and one maybe has some hope of computing computing entropies of black holes and so on. There's a lot to be done. We don't know various things. So, for example, which unsharp time observables yield type reduction. So we just have a sufficient condition. We also don't know. Exactly what kind of quantum reference frames will emerge out of quantum field theories. So this is somehow artificial. We have a quantum field theory, but a quantum mechanical reference system, which is a little bit artificial. So there's a lot of activity going on to try to understand exactly how to intrinsically define quantum reference frames in quantum field theory. As you noticed, I did not say gravity. It's not clear that gravity plays any role here at all. It seems to be much more about the type of quantum reference frame that is admitted from the isometry group of the space-time. So there's a lot to do, is the take-home message. I think the two most pressing things are quantum reference frames describe themselves by quantum field theories. What are their properties? But there's also an interesting idea of sort of starting from scratch and saying, could we go to a 2-1 directly, somehow axiomatically or in some relational way, just starting from without, it's a bit of a business to take you take a quantum field theory, to take a quantum reference frame, we find out the invariance, blah, blah, blah. It seems like maybe there should be a more direct way to get to these theories straight away. So I think that's all I have to say. I'm sorry that I'm slightly over. And here are some extra references in some of the main papers. So thank you very much for listening. Yeah, that's it.
Okay, thank you very much for this very interesting talk. Are there any questions, comments, remarks?
Yes. So I'm happy to learn that N is so powerful and to make type 3 things into type 2, 1, whatever. So, but to be honest, I want to understand physics going on here. What is physics? I mean, what picture should I have about this introducing quantum reference frame and making type 3 into type 2, 1, which looks much better?
Yeah, that's a very good and I'd say semi-open question. So I would say that we, or at least I, don't have a good understanding of exactly what is happening. So, just because the resulting theory is type 2, 1, well, the observer has somehow become muddled in here. So it's not that we're saying that the system that is now being seen by the observer is type 2, 1. It's somehow they're all part of it. So it's somehow that maybe somebody from the outside will say that it's 2, 1. But how do we argue that? One needs to bring in another observer to say that the system that they see is 2, 1. And what does it mean that a 2, 1 is more like a quantum statistical mechanical system rather than a quantum field theory? I don't know at the moment. So at the moment, I'd say, yeah.
The resulting theory depends on the quantum reference frame that you introduced, and there is an arbitrariness.
Yes. Yeah.
And can I imagine that this choice depends on like what kind of observation you make and what kind of, I don't know. Does it correspond to the vague notion of observer in quantum mechanics or something more than that?
Yeah, also a very important question. So I would say that there's less arbitrariness if the quantum reference frame is supposed to itself be a quantum field theory. because they're much more constrained somehow than quantum mechanical systems. So we don't know what happens in that setting. So we bring in a quantum reference frame in order to say, well, we want to say that the invariant observables are somehow accessible, or to say, well, how do we deal with non-invariant observables in some sense? Well, we introduce a quantum reference frame and we say that, well, the total thing is invariant, even if the thing that's being looked at by the quantum reference frame is not invariant. Now, in what sense the quantum reference frame is itself, say, a measuring apparatus in the sense of quantum theory of measurement is not completely clear. In my mind, those two things perform different tasks. A measurement apparatus has to somehow reflect the properties of the system being observed. And a quantum reference frame has to, in some sense, invariantize the system being observed. So we want some system that maybe does both. It's not clear that a single system can perform both tasks. But I would say that, the exact role of measurement in quantum reference frames is also open.
Okay, thank you.
So again, like I don't have good answers. I think that, well, that's partly why this is an invitation, is that I think there's most questions that can be asked are in some sense still to be done. So I think there's a rich area for further work, I would say.
Okay, thank you.
May I ask a question?
Yes.
I think in your framework, the choice of this quantum reference system is essentially free.
Yes.
So there are these attempts to understand measurements at, say, Planck length size to be unsharp due to effects of quantum gravity. So one could try to use as a quantum reference system a system of non-commuting coordinates.
Yes.
Would this be natural in your approach, or could
Yes,
you
absolutely.
contribute more insight on this?
I would say no good insight, but I mean, my sense is that when we do this in quantum mechanics, there's a sort of the traditional view is that yes, the reference frame is in some sense arbitrary. I mean, one might have some constraints given the actual experiment that one is doing as to what is the actual reference frame, right? But if one can sort of design and construct things arbitrarily well, one can always make the frame as good as possible, i.e. basically L2 of G with canonical PVM. But what's interesting here is that that's not what you want. To get this say good behavior of the finite trace, one wants some intrinsically unsharp observable, some POVM that's not a PVM. So my feeling is that the direction of travel should be what are the natural ones of those that are given to us from our physical theories, which might be quantum field theory in curved space-time, it might be quantum gravity. So it depends what we're trying to do. But my hope would be that, I mean, I suspect that some unsharpness comes sort of for free in those theories. So in the CLPW example, it comes just because they chose the Hamiltonian to be semi-bounded below, Q plus. So you say, well, we could choose it to be something else, and then we don't get this behavior. But my feeling is that in the more proper theories of exactly as you say, quantum field theory or even quantum gravity, where something fundamentally different happens, one is not going to be free to choose those quantum reference frames arbitrarily. They should be described by the theory. But how to do that is not completely clear to me. Of course, there are some good examples. I'm aware of your work and some other work that does describe covariant POVMs in those settings in a little more generality than I've discussed them here. But I'd say that's also future work. So yes, it should be done. It's the natural thing to do, but we haven't done it yet.
Okay.
Okay, any other questions? Okay, well, maybe let me ask a question. So you mentioned gravity only in the last line. I heard about, I happen to hear about quantum reference frames mostly in the context of quantum gravity, like we need them to introduce time, the sort of statement. So my picture was somehow that in quantum gravity they are maybe really needed because quantum gravity is something I don't know. So maybe you need them badly there. And in other theories, it's maybe more like luxury. Let's make things even more, even nicer. Is it like this that they naturally come from quantum gravity, or you are saying that to the opposite, they are not naturally everywhere? Or are there more badly needed in quantum gravity than in other contexts? Or
Yeah,
not
I
really.
mean, there may be people here who can answer that better than me. So, I mean, my understanding is that yes, they are needed in quantum gravity. Um, I mean, certainly if one wants to write down diffeomorphism invariant things, one's going to have something like this, I would say.
So the bigger symmetry group, the more badly I need quantum reference frames. Is it like the rule of the thumb or not really?
I think that's reasonable. Yeah. Yeah, I
Okay.
think that's reasonable. I mean, I also am not an expert in quantum gravity. I'm certainly not trying to say that they're not needed there. This was a technical comment about the type reduction.
Mhm.
The gravity didn't play a role in obtaining this 2-1. However, certainly I think that the consensus, as I understand it, is that um, for building relational observables in quantum gravity, which should be in some sense diffeomorphism invariant, these sorts of ideas will play a key role. There are people who have gone much further than that than I've been able to. They have a stronger background in quantum gravity than I do.
Hmm.
Um, so I guess my approach is to do things slowly and carefully,
Hmm.
um, and see how far I get. But there are ways where you start at the top and see, different approaches to doing this. So I'm moving in that direction. I think they will play an important role. Problem of time and so on.
Hmm.
Wheeler DeWitt think even things like this are related to, or I think will
Uh-huh.
include quantum reference frames in their resolution or in some compelling narrative about how we should understand diffeomorphism, invariant theories, and so on. I just haven't got that far yet.
Okay, I'm asking because we had a talk of Edward Wheaton in this seminar, I think several years ago, and if I remember correctly, I mean, roughly his comment was that in quantum field theory, the algebras are type 3, and then in quantum gravity, they should be type 2 or something. The type should change. So now in this quantum reference frame papers, this when this quantum reference frame situation was a type 2, and without quantum reference frame I had type 3. So I always thought that this quantum reference frame should be sort of a toy model of quantum gravity to be consistent with Witten's comment. Is it like this or?
So the that I mean, I'm not sure. I guess he was maybe talking about this paper that I discussed, where you have the type change from the 3 to the
Yeah.
2. So they do mention gravity in that paper. It's not
Uh-huh.
completely obvious to me that it's used. So they have the cross product plays the same role as it does in what I've described. They say that there's a gauge constraint
Uh-huh.
um, that that plays a crucial role, but it's not clear to me that it does. And I think what we've shown is that it doesn't maybe play
I
a
see.
crucial role,
Okay.
which is not to say that gravity uh, in quantum gravity is not somehow a very important feature in the milieu of things that we're talking about. But I think in this example, it wasn't obvious that gravity played played a role at all. But I noticed that Topos York has a raised hand, so I feel like one of the experts there might have something to add here.
Yeah, so please, Topos York.
Can you hear me?
Yes.
Okay, great. Yeah, I wanted to comment on that because I think that's a bit subtle with the statement that quantum gravity is type 2, because this example that, well, Edward Witten talked about and now Leon talked about in the context of our paper, it's a very fine-tuned situation that you have the modular action of the time translation. So, and this is crucial for this type 3 to type 2. So I think we are very far from, being able to prove as an actual theorem that you can always get this modular action when you consider the space of invariants under the homomorphism group. Because I mean, sort of aspirationally, what Leon was talking about with this group G should be suddenly the diffeomorphism group, but this is, not really as locally compact as you would like. So, on the technical side, this is already big step. So I don't think we can really say with confidence that gravity is type 2 on mathematical grounds. Yeah, but I mean also the other point about, well, the Klaus's question essentially about these dynamical coordinates. So I mean my hope is that what we have done 10 years ago with Klaus and Romeo about gauge invariant relational observables for quantum gravity, that this can be put into this framework of quantum reference frames. But this is also a work in progress. As Leon said, we have a lot of work in progress. But I guess that's a good thing. And yeah, I mean, hopefully that all comes together, because conceptually I think this is the way to go, but yeah, there's a lot to be done. And yeah, I mean, in quantum gravity I think you really are forced to look at relational things, because there are no gauge invariant local observables, so you have to look at relational things. So I guess the statement that, I mean, you need QRFs in quantum gravity is really that, well, otherwise you're running low on observables. So the less observables you have sort of on the nose, the more you need a QRF to help you out. Hi, Aldo! Okay, thank you. Topos York, over.
Okay, thank you very much for these comments. Very helpful, yes. Any other questions or remarks? Yes, Aldo.
Hi. Hi, Leon. Just maybe another question inspired from quantum gravity, but as can be reformulated in any context. So in quantum gravity, if you have it couples universally to everything. So you cannot have uncoupled system that you just tensor, but the Hamiltonian kind of is block diagonal. And so another way to put it is that anything back reacts in gravity. So it does, does it play a role in any way in what you told us today, or?
No, simply for the reasons that I gave. But you're right that, I mean, yeah, even this tensor factorization is complete nonsense, obviously, in general, right? That we can't just do this. On a technical level, I think there is hope to define quantum reference frames in a more general way for von Neumann algebras, where you can at least separate out something like commuting subalgebras, and one of those commuting subalgebras could function as one of those subalgebras could somehow function as a QRF for the other algebra that it commutes with, or something like this. So I think that the tensor factorization is not crucial. Of course, I still haven't. Also, it's yet another thing that I haven't done. I think there's hope to do that. I don't know if that's the right thing for what you're saying, but at least it would be more appropriate, say, than just tensoring in an arbitrary second system and calling it a quantum reference frame. I think that's
and from maybe does the Hamiltonian evolution an Hamiltonian evolution which is not block diagonal in what you described would play any role, or anything would just go through with coupling between the system and the reference frame?
I have no idea, honestly. So yeah, I think I can't say anything. Somehow the entire framework is based on somehow some sort of separation. So I think, yeah, I don't think I know enough about quantum gravity to say something sensible.
No, I meant even in quantum mechanics, like in this vanilla version, where you can tensor things, and I was just wondering if a non-block diagonal Hamiltonian changes the picture or is completely irrelevant to what you presented.
There does exist work on that, not by me, I think by Philip Hearn and so on, where they have interacting clock, or maybe Alex Smith interacting clocks and so on.
Okay.
But in this work, no. So
Thanks.
that's yeah.
Okay, there is another question from Topos York.
Hello. So it's just a comment really on the role of gravity. In the Whitton paper, they indeed start talking about gravity, but then they immediately say, think of it as weak. So I think that the strongly coupled aspect that Aldo was referring to is immediately taken out of the picture. And of course, for full gravity, you would have diffeomorphism invariance, but they're working on de Sitter. So you haven't got, and really as a given manifold with fixed metrics. So instead of full diffeomorphisms, you're really down to the isometries of the de Sitter static patch. So really, what you're left with is a relatively small symmetry group, which is a sort of broken version of full diffeomorphism invariance. And that is because firstly, they've chosen what they call weak gravity, and then that they've gone to a de Sitter background. So it is, as Kasia was saying, it's quite a special situation. I think that part of our idea is that you can apply a similar thinking to any quantum field theory in a curved spacetime. We're used to thinking of quantum field theory and curved spacetime as living on a manifold, but that is somehow not the picture of spacetime that you should take from general relativity. If you take the whole argument seriously, and you should take account of symmetries. And if you apply that same thinking, you for any quantum field theory would have the same picture, that you should invoke a reference frame and then have this change of type when there are symmetries in the background. So thanks. That was the comment.
Okay, thank you very much for this comment. So, any other questions or remarks? Okay, if not, then maybe let's thank the speaker again and stop the recording and have a few minutes for stupid questions.